Thanks for giving me a chance to make this presentation and talk about this interesting topic. My name is Vlad Orlov. I work in PayPal, where we personalize everything we can, so to speak. Recently, I've been working on the machine learning project. In fact, it's a machine learning library for Rust that provides out-of-the-box implementations for many popular machine learning algorithms. But this presentation is not really about this project. It's more like a consequence of this project. It's a result of this experiment, because what I realized while doing this, working on this library, is that a lot of machine learning tools and algorithms can be implemented in Rust if you use the right set of tools for that. And my goal today is to talk about these tools, share those with you, and walk you over the process of building two very simple machine learning algorithms. And my hope is that with this, I will show and demonstrate a couple of common approaches that you would be looking into and using to implement your own machine learning algorithms. And along the way, I'll demonstrate a couple of libraries. Oops, I think I forgot to switch to the presentation. And by the way, I probably need to start sharing screen before I'm too far into the algorithms. And my hope is that with this, I will show and demonstrate a couple of common approaches that you would be looking into and using to implement your own machine learning algorithms. And along the way, I'll demonstrate a couple of libraries. Oops, I think I forgot to switch to the presentation. And by the way, I probably need to start sharing screen before I'm too far into the. Can you guys see my screen?
Yep. Yeah, looks great.
Okay, so I'm gonna go to the next slide. Oops. All right. So the agenda for today's, as I said, to talk about, I'll talk about the process of building a simple regressor and a classifier in Rust. And along the way, I'll talk about an algebra, ND-array, and argmin libraries. A little bit about SmartCore. Not so much. This talk is not so much about the last library. And the one more thing is this is a repeat of another talk that I gave in the Seattle Rust meetup. So if you've seen that presentation, this one is it's pretty much the same thing, a little bit shorter. I fixed some of the errors and mistakes that I've made, but if you've seen that one, this one is going to be not that interesting to you. And a couple of other disclaimers. So in this presentation, I'm not talking about, well, first of all, you should be on board with this idea that Rust is great for scientific computing and machine learning. I'm not going to convince you in this. And this talk is not about the deep learning or large-scale machine learning or any other accelerators that are out there. So this is just how to build a very simple logistic regression, linear regression in Rust with pretty much using standard Rust, no other, well, and a couple of libraries, nothing more complex than that. And so if you don't have a prior experience to machine learning, then here's a quick refresher on the basic concepts that we'll need today. Well, first of all, I want to answer this question. What is statistical learning? So let's say we have some response, a quantitative response, basically some number that we want to predict. And along with this number, we have some attributes. These are usually, in machine learning, we call it features. Sometimes it's called dependent. Well, y is dependent variable. all these x1 and x2 and so on and so far are independent variables. So these are our predictors. And these predictors correspond to the response y. So for example, let's say you have a house and the house has a price. That's our y. That's some concrete number, right? And each house has certain number of rooms, certain number of bathrooms, and some other attributes. In fact, those attributes are not necessarily quantitative. Sometimes it might be a class or a type or something that represents particular quality of this house. For example, it might be the type of the heating system that is used in this house, or the location. And the attributes of this house are called predictors, while the price is our dependent variable, our response. And what we think is that there might be a relationship between the predictors and the response. So if you think of predictors as a vector, it might be either a column vector or a row vector, it doesn't matter. And our response, y, is our price, is just a number, scalar. What we assume is that there is a relationship between this vector with the predictors and our response y. And this relationship is usually expressed as a function in machine learning. Here is just a generic y equals f from x, where this epsilon here is just some irreducible error. So when we model this relationship between y and x, we usually model this as a function with some noise added to this function. And that's all that this expression represents here. And usually we don't have just one sample, one house, but in machine learning, we usually get our hands on, or we work with the larger data sets where we have many houses or many many vectors with predictors that combined together give us a data set. And what we do, we train our machine learning algorithms on these data sets. We learn the relationship between x and y, and that becomes our model. So in this case, for example, that's an example of the Boston housing data set, where it's a pretty standard data set in machine learning. And here in this data set, we have houses. Each row represents a house. And on the right side of this matrix, you can see the column with the price. That's our dependent variable. That's our outcome or response. And you don't really have to understand what are these attributes. It doesn't really matter for us. I mean, when you are cleaning the data set, when you are preparing the data set for machine learning, it does matter, of course. But in this particular case, you can think of it as just some numbers that has some relationship with the price. So why do we use statistical models? Why do we need to train the model, build and design statistical models? So we design them to solve concrete problems, and there are multiple ways to categorize these problems. For example, when you have a house price in your data set, you can use supervised learning to train a model that can predict the price of any new house in the same area from the set of the new attributes. But when the house price is not available, we can use as unsupervised learning to better understand the structure of our data. For example, we can split our data set into multiple clusters, and the hope is that the houses in the same cluster will share the same attributes, the same will be similar. The items in the same cluster will be similar. Another way to categorize the statistical models is by the type of the target variable, by the type of Y. When it is a number, like a house price, the machine learning model that predicts this, the value, the number from the new data is called a regressor. And when the dependent variable is categorical, like spam versus ham or red versus blue, the algorithm that we are using becomes a classifier. So today, by the way, we're going to build one classifier and one regressor, but we're going to use the same algorithm to do that. Well, not the same, similar algorithms. Now the question is, how do you choose the model that captures the relationship between X and Y? And what are the parameters of this model? Because the model has to be parameterized. And what assumptions do we make when we design our models? How do we estimate the parameters of the model? So these are all the quick key questions that you ask yourself when you develop a statistical model. And when you solve a machine learning problem, first thing you try is to understand what category this problem falls into. Is it a classifier, for example, or regressor? Or do you have the dependent variable or not? Because if you don't, maybe you are limited to the unsupervised learning. And then the question, then you might ask yourself, what kind of algorithm can I use? What assumptions can I use? What models fit my data better? And to answer all of these questions, you will need to analyze your data and do some exploratory analysis that I'm not going to talk about it here. But the other thing that you might need usually is some kind of a library or a tool that will help you quickly go through multiple machine learning algorithms that can be used to this library can be used to quickly fit your data to a certain type of the model and to see what's the performance of this model, what's the predictive power of this model. And languages like Python and R are famous for these kind of libraries. What you will see, for example, in Python, I don't know whether you're familiar or not, there is a very, very popular library that's called scikit-learn. Of course, you can use other libraries like TensorFlow and stats models that are also available in Python. So Python is really great in providing this kind of tools. R was pretty much built for data analysis and statistical modeling. So you will find a lot of big and small packages that provide these sorts of libraries out of the box. But what about the Rust? The question is, do you have? Can you use Rust to design and implement your statistical models? And the good news is that in Rust you will find libraries that cover two big areas in mathematics that are really important for machine learning. The first one is linear algebra, and the second one is optimization. So one library that I'm going to talk, two libraries that I'm going to talk about today are, they belong to linear algebra. You can do a lot of you can manipulate arrays, n-dimensional arrays, and apply a variety of methods that come from linear algebra to your data. And the second library I'm going to talk about is it is really great for running all sorts of optimization on your algorithms. And in this presentation, now we are finally getting to something concrete. in this presentation, and by the way, maybe before that, let me know if you have any questions. I will be really, really happy to answer those right now before jumping into something more concrete. All right. So if there are no more questions, no questions, and I don't see the chat, so let me check. Actually, yeah, there are no questions in the chat as well. So what I'll do, I'll talk about the first concrete machine learning algorithm that we will implement today in Rust. It's the linear regression. And it falls into category of linear models that assumes a linear relationship between X and Y. If you have just one predictor, if you have just a scalar, for example, weight, and your target, your dependent variable is height, for example. So the linear relationship it's very simple to represent. It's just a line. So when you are all you need to predict height from weight is to see where the point on X projection from some point on X intersects the line, and that's your prediction. That's your Y. So you kind of see where X. Let's say you have 0. Well, let's say this point on X is 2. You see where it intersects Y, and that's your prediction, that's your height. If you have multiple, if you have more than one predictor, let's say in this case I have 2 for each sample, then your line becomes a hyperplane, and the equation that you use to predict Y becomes slightly more complex, but it's essentially a linear combination where you start from, where you still, by the way, I forgot to talk about these parameters, right? So beta 1 and beta 0. So what are these? These are parameters of our model. Each model will have, when you train your algorithm, you will end up having different values for beta 1 and beta 0. And these values will depend on your data. Depending on your data, you will find the right slope of the line and right intersect that fits your data the best. So the training is basically figuring out what are the values for beta 0 and beta 1. And when you have multiple predictors, when your X is not a scalar but a vector, this task of finding parameters becomes slightly more complex. But the good news is that there are methods for that. And even better is that in Rust, we have libraries that can do that for us. So once you found the values for your parameters, beta 0, beta 1, beta 2, all you need to predict Y is to run it through this formula, do this linear combination, add it up. Once again, the epsilon is our irreducible error. Some portion of this error comes from the fact that linear model is not perfect. Even for the weight and height example, even though there is a linear relationship between weight and height, usually, it's not always the case, right? So we will have outliers and certain individuals that don't fall into that don't necessarily can be height of which we won't be able to find through the very simple model. Let me actually see what's the next slide. Okay. Okay. So now I will let's go to the first we'll go to the Python, and I'll just quickly show how will I feed linear regression to the Boston housing data set, the data set that I've showed earlier. So first of all, I mean, that's just how I load the data set. This function load data set, it comes directly from scikit-learn, one of the libraries that I've mentioned that provides a big selection of machine learning algorithms. So I'm loading this data set, and right away I'm displaying this data set just to make sure I've loaded it correctly. And as you can see, it's exactly the data set that I showed previously in on one of the slides. Let's see. So then what I'll do, I'd like to split my data set into X and Y. My X are predictors and Y is dependent variable. So I'm basically just taking my data set, Boston housing, I'm dropping price from it, and that becomes my matrix with predictors. And then I'm taking price, and that becomes my column vector with the target, with the dependent variable. I'm printing out shape just to make sure it all looks right. And then what I'll do, that's a standard procedure. Basically, what I want to do, I want to split my data set into training and test. Why do I need to do that? Is because I want to make sure that whatever estimate of performance that I get for my model is not biased. So I'm going to train my model on the data set, on one data set, and then I'm gonna use the other portion of the data set to see, to estimate the performance of the model. There are better ways to do that. That's a very simple way to do that. And if you have a big data set, like let's say hundreds of millions of rows, that's pretty much the only way you're gonna use. There's another way that's called cross-validation. As I said, for the big data sets, cross-validation is probably not gonna, well, you still might want to use that in certain scenarios, but if all you need is to get a rough estimate of the model performance, the simple train test split will be sufficient. So this function, by the way, it also comes from scikit-learn in Python. And this test size is the share of the portion of the data that I want to leave for testing. So I set aside 20% of data for testing, 80% for training. And once again, I'm just printing shapes of the data frames here just to make sure all feels right. For the training, I have 404 samples, and for test, I have 102 samples. These are number of attributes, by the way. So each house is represented by 13 numbers. And now I'm going to feed the linear regression just using a standard linear regression class from the scikit-learn. With scikit-learn, it's a really easy thing to do. You just fit your linear regression to your training portion of the data, where X train represents the predictors, Y train represents the dependent variables, the outcome. And then I'm going to use mean absolute error to estimate the performance of the model. Basically, what this formula is about, it compares the actual outcome, because I know for the training, for the test set, in test set, I still have my outcome. I still know how much the house costs, right? And Y hat is the estimate of the price that I've got from my model. So what I'm doing here, I'm just taking the difference here And then I'm taking the absolute value of that, and then I'm adding it up together. So the bigger this individual, the bigger this difference here, the bigger the error I'll have at the end. The bigger my mean absolute error will be. And by the way, here's I'm averaging it over the number of samples. So when I apply that function, when I'm running the mean absolute error against the predicted value and the real value, that's the number I get. So on average, my model will be about I don't know, it's dollars probably. Well, maybe not dollars. I'm not sure what's, let me see, what was the 21? I think there was some kind of I don't remember the unit for the price here, but on average we will be 4 units off when we are using our logistic regression to predict houses in the Boston area. And finally, what I want to do here is just to print out the coefficients, because I'm going to need it later to show you the difference between this model that we've just trained in Python and the model that we will train in Rust. These are the parameters. These are the betas I've mentioned earlier. Since we have 13 predictors, each of these predictors gets its own multiplier. So these parameters are these multipliers in the linear combination, and the intercept is our intercept value. So the question now is, how do we find those parameters? Like, if I want to implement that in Rust, what will I do? How will I? The biggest question here is not how to implement the predictor, the function that will give me the price of the house if I know the parameters of the model and the parameters of the house. But the question is how to find the parameters of the model from the data, from the training data set. And luckily, if you know linear algebra, it's really easy to do, because if you look at this equation that we have, the logistic regression equation, this one, right? If you look at this equation, there is a very straightforward way to solve it. If you take, all you need is to multiply both sides of this equation by inverse of x. X is our matrix with the predictors. So all we need to do is to multiply from both sides by inverse of x, and and we get our estimate of beta. The only problem is that in reality, what you want to do, you want to actually do it a little bit differently, because if you'll try to find an inverse of this matrix, you probably won't be able to do that. What you want to do instead is to do some additional. You want to transform the tall and skinny matrix with the predictors into the square matrix first, because it's guaranteed that while you're not guaranteed to find the inverse of the tall and skinny matrix, you will be there will be no problem in finding inverse of the square matrix. And basically, what I'm doing here, how have I got from here to here, is by first multiplying everything by x transpose. And then once I have that expression here, all I need now is to find parameters of the model is to move this portion of the equation to the right by multiplying both sides by inverse of x transpose x. And that's the expression that we're going to use to find estimates of the parameters of the model. So let's just do that in Python first. First, actually here what I'm doing, I'm transforming, I'm doing one additional transformation because if you remember, the model is represented in our case by the coefficients and the intercept. So what I want actually is to make sure that I add one additional column to our parameter, to our predictors. And by just doing this, it will be a little bit easier to get intercept in just one go instead of finding it later. So here I'm just preparing the matrices for the inverse, and then I will use the NumPy inverse to find the estimates of the model of the beta. Sorry for the confusion here. So X hat here is actually should be called beta hat. I think I forgot to fix that. But once you have the estimates of your model, you can split into coefficients and intercept. And if you compare the coefficients and the intercept that we've got with the previous coefficients and intercept, you'll see that we are getting exactly the same numbers. So we are moving in the right direction. But that's not all. So in reality, if you will look into how the scikit-learn finds the estimates of the model of the logistic of the linear regression, you will see that they don't actually do the inverse, because inverse is a very costly operation. If you'll run inverse on a really huge matrix, you will wait for quite some time. Although although it won't take too long, right? But still, you want to save as much time as possible. And also the other important thing here is that if you will run the inverse on the big data set, your estimates, you will get some, you might get an issue with the precision. And the reason for that is because, the procedures that is being used to find the inverse of the matrix, it consists of multiple operations on this matrix. And the more operations you make, the more imprecision will creep into your estimates, your parameter estimates. So the basic idea here is that you want to decrease the number of operations. You want to make the inverse. You will still have to do the inverse, but you want to make sure that you take the inverse of on the matrix on the matrix that is as small as possible. And in this particular case, what you do, you take X, you take your predictors, and you split it into two matrices. The first one is has the size of n by n, and the other one is the upper triangular matrix that has zeros at the lower bottom part of the matrix. And because of that, the inverse, it's much easier to find the inverse of this matrix. So you'll basically have to go through smaller number of, these plus, minus, multiply operations on the elements of the matrix. And the Q transpose is also very, very straightforward to do on matrix Q. So this method is called QR decomposition. Of course, you still need to do a lot of operations to decompose the matrix, but it's more numerically stable than just taking an inverse on the original matrix. And in fact, you will see that in scikit-learn, they provide, I'm not sure you can choose that, but under the hood, they use not only QR decomposition, but they use all other decomposition methods to prepare the matrix for the inverse. And in Python, if you do that, it's actually, in Python, it's actually very, very straightforward thing to do as well. So instead of just applying inverse to my matrix like I did before, what I'll do first, I'll decompose my matrix A into Q and R, and then I'll apply this formula. Oh, sorry, not this one. This formula directly to R, Q transpose, and I get my coefficients again. And if you compare them to the previous estimates, once again, we've got the same numbers, so we're moving in the same direction. And now the question is, if I go back to my slides, the question is, how would you do that in Rust? So now we are ready to solve this, to fit linear regression in Rust. But in order to do that, if you remember, in the Python code that I've showed you, it all boils down to inverse. And a little bit, and also, having some library that helps you to manipulate n-dimensional array will be really, really great, because you won't have to run through loops to, for example, extract the predictor, the column with the predictors from your original data set, and so on and so far. Or for example, if you want to do transpose, you once again, you won't have to run through multiple loops to do that yourself. So what you want is to have some kind of a library that provides methods that help you to manipulate multi-dimensional arrays, and also you'll need a little bit of methods to decompose the matrix and to apply inverse on a matrix. And the good news is that in Rust you will find two great libraries. One is an Algebra, and other is NDArray. I actually like NDArray a little bit more, simply because it's I think it's designed at the same on the same principles as the NumPy, and NumPy is the pretty much cornerstone project when it comes to machine learning in Python, because a lot of libraries, even scikit-learn, relies on NumPy for many transformations and under the hood magic that happens when you apply linear regression, logistic regression, or any other machine learning methods to your data. But on this slide, I've just have a bit of a comparison between these two. So the biggest difference is that I would say the reason why all the examples that I'll show today are using an Algebra is pretty much the printout method. So the way if you try to print an Algebra array, it will be displayed in a really nice manner, where you can see right away what are the values in your array. But really, all the examples that I showed today can be you can use NDArray as well. You'll just have to figure out the corresponding methods that I use, alternative methods that I use. The method corresponding methods to the functions that I use for inverse and matrix decomposition. And now I think we are ready to go to the Rust regression. So here, what I'll do next is I'll take the data set, the same data set, and I'll feed the linear regression to the data, and hopefully the results, the outcome, which is the parameters of the model and the performance of the model, will match the performance of the Python model that we've seen so far. Are there any questions or comments or Anything you guys want to share?
I had a question. You mentioned those two libraries. Are they about the same in abstraction level, or is one easier to use than the other?
I would say the ND array is designed around the idea of having that you don't have just matrices and vectors, but you want to work with arrays that are, let's say four dimensions. So if you are doing a machine learning, I would say the ND array is a bit more easier to use, so to speak. And also, as I said, ND array follows some of the concepts and ideas and function names that can be found in NumPy. And for those who are doing machine learning NumPy, they are very, very much familiar with NumPy. So going back from NumPy to ND array would be much, much easier. And algebra, I think the algebra was designed for the computer graphics. That's my feeling, at least. I don't have a confirmation of that, so don't take my word on that. But I would say that, well, another interesting difference is that you will need BLAS and LAPACK backends if you want to work with the ND array. And for example, on my Mac machine, I wasn't able to compile ND array with the BLAS LAPACK support. And what are these? These are really important backends if you're working with the huge arrays, because just using the standalone implementation to, for example, find an inverse of the matrix without BLAS and LAPACK will take longer than with this backend. In an algebra, there is so the some of the matrix decompositions methods won't work without BLAS and LAPACK in ND array, but in the algebra you will have no problem with that. So they provide the out-of-the-box standalone implementation that you can use to run the matrix decomposition and other linear algebra routines on your data.
Does that end up being slower though for equivalent transformations? Okay.
Yeah. So if you use the backend, the LAPACK backend, it's faster. I'm not sure why though. I think I don't know why. It's a good question why. In theory, it shouldn't. I think it's just that the libraries, these libraries were built in Fortran for many, many years, and people have spent a lot of time and thought into optimizing the routines. So they still work faster.
Yeah, that's exactly it. It's been optimized really, really well for a very long time.
So, but here in this presentation, and by the way, I'm not using BLAS and LAPACK, so it's that's another reason why I'm using an algebra. So what we're going to use, as I said, we're going to use an algebra, and this crate smart core. There's just one function that we're going to take from this crate. It's the library I've been working on. Basically the idea around this library is to provide out of the box implementations of the popular machine learning algorithms, just like scikit-learn. But we are not going to use any of these today. So so here I'm just doing a little bit of an import to declare the classes that I'm going to need for data pre-processing and running my inverses. What I'm going to do, I'm going to read the file with the data. That's my Boston housing data set. Trust me, it has exactly the same data as I've used for the Python example. So this function, you will find it in the code that I'll share later. What it does, it reads the file and it transforms it into the type that is provided by the algebra. This type represents a matrix, a n-dimensional matrix. Since we are reading a CSV file, there are just 2 dimensions for this matrix. the values that I'm reading back are all floats. And I'm printing out the shape of this matrix. We have 500 examples and 14 attributes. Why 14? Because 13 predictors and 1 dependent variable. And just to display how it looks like, remember I've told you that when you print out an algebra array, it's printed out really nicely. You can see each number separately. And these are our house prices. The right column is our prices. Then what I do, as I did in Python, I want to prepare my predictors, separate my predictors from my dependent variables. Once again, I'm printing out shapes the same way I did it in Python. And as you can see, it's really, really nice to have an algebra do a lot of work for us. Essentially, I'm following the same path I took in Python at this point. Oh, I see there's a question.
There's a quick response time. I was just wondering if this stuff all gets loaded eagerly, or is it like like data frames or something where
yeah,
it can stream?
You are loaded. It's not lazily loaded. It's loaded right away into the memory.
Gotcha. Thanks.
What I'm gonna do next is, well, once again, I'm just printing out the first 5 rows of the data of the predictors and the first five prices. And now I'm gonna do the train test split. That's where I'm gonna need to use smart core, because there's an algebra won't provide you with this function. So this function works exactly the same way as scikit-learn's train test split. I'm reserving 20% of data for test and 80% for training. And now we are ready to run our inverses. So the first thing that we're gonna do is we're gonna use the simple inverse as I did in first Python example. So I'm preparing my A and B. A is my matrix with the predictors plus 1 additional column to quickly estimate intercept, and the B is the outcome. Well, let's just again print out. So now what I'm gonna do is I do A transpose A. ATA is A transpose A. Remember, I need to transform my tall and skinny matrix into the square matrix. Otherwise, I won't be able. It's very likely that I won't be able to find an inverse. And then I'm applying the inverse to my A transpose A. And the function, this try inverse, it comes directly from an algebra. There is a corresponding method in ND-array, but I think you're going to need to have a LAPACK and BLAS backend for that. In an algebra, it comes out of the box, so you don't have to do anything special. Just import an algebra, and you can use it right away on any matrix. This unwrap is of course necessary because once again, it's not guaranteed that you're going to find inverse. In this case, it is because we have a nice and easy square matrix, but you know, you still need to do this unwrap because it's not guaranteed. And then I'm just following the formula that I've shared earlier. I'm multiplying my inverse with the A transpose, and I'm multiplying that with the response, with the column that represents the response. And then once I've got x hat, I'm splitting it into coefficients and intercepts. And let's look into the values that I've got so far. So here, these are the multipliers that I've got for all 13 attributes, and that's the intercept. So let's look into that. Let's compare that to the Python code. As you can see, although it's not exactly the same, we've got numbers that are really, really close to those numbers, to those estimates that we've got in Python. And the reason why it's not the same is because when we do train test split, we are randomizing our data. And because of that, the train test splits that we've got in Rust are not exactly the same train test splits that we've got in Python. So the numbers will be different. The most important thing here is that they are really, really close to the origin, to those that we've got in Python. And that's how you're gonna use the linear combination to get the estimate of the house price. So let's say you have a matrix with your test data where each row represents an individual house and each column is an attribute of this house. So what you have this matrix of X test. That's your predictors. You multiply it by coefficients, and then you add intercept. And that's all you need to do to do the forward run of the model. Finally, I'm going to use the mean absolute error to see how the performance of this model differs from the performance of the model that I've got in Python. And as you can see, we've got even a better error, but it doesn't tell a lot, right? Because of the randomization, next time I'll do the train test split, I might get a higher number, I might get slightly lower number. But what is important is that, I don't remember where it was, but I think even here, maybe here. Let's compare it to the mean absolute error that I've got in Python. So in Python, I've got 3.44. And in Rust, I've got 2.9, which is also really, really close to 3. So that tells me that, we've got the model that has unpaired performance with the Python, which is good. But the question is, can we actually do the decomposition as well? Use this better approach to fit the linear regression to our data? And yes, of course we can. Both Algebra and NDRA provide the variety of matrix decomposition methods. And by the way, you can use not just the QR decomposition, you can use other decomposition methods here instead of QR. I think by default, scikit-learn uses SVD decomposition, but it doesn't really matter. So, because both NDRA and Algebra has SVD decomposition as well. So that's just to show that we can find the estimates using the other methods, and that the estimates we get are exactly the same. In fact, they are, I think, yeah. So you can just look at the intercept. It's we've got exactly the same number when running through the other methods. And once again, if we apply the forward run, we will try to predict the outcome, the prices, and compare it to the actual prices. We will see that the mean absolute error is also the same. And that's pretty much it about the linear regression. And the other method that I want to talk is the logistic regression, which is really, really similar to the linear regression. There's a little bit of a difference. The biggest difference is, of course, how we find the estimate of the model, the parameters of the model. And if there are no questions or comments, I'll probably go.
There was a question in the chat. I don't know. You don't have to. Maybe it's something it'll make more sense near the end. But earlier, someone had asked for a general comparison of using dynamic type languages versus static type language for doing this kind of work. But I don't know if you get into a more general comparison where that would make more sense to do.
That's right.
I would say.
Yeah.
Sorry, go ahead.
Yeah, no. I kept that question in the end of the session actually. So yeah, comparing the dynamic type languages and the Rust has the static type language, right? Like, what are the challenges which we face actually, or like you faced using the Rust compared to Python or?
I would say at the very high level, using languages like Python are that are dynamically typed, that have this duck typing model. It's very, very easy to use those for prototyping, for fast modeling, for data exploration. And the reason is because you're not slowed down by the unnecessary, in this case, by the language. You're not slow. You don't have to think about types. You don't have to make sure that whatever transformation you're doing has only floats or only integers and so on and so forth, right? So if you are prototyping, if you don't know what concrete algorithm you're going to use, I would say go ahead and use Python or R to first experiment, to first model what you want to do, and come up with the concrete pipeline, concrete algorithm that you will use. And once you have the concrete pipeline, you can start thinking about replacing certain parts of this pipeline with the Rust implementation, if you can, because in most of the cases, I would say nowadays a lot of the Python code boils down to calling C++ routines. So you will probably get the same performance most of the time, but not always. There are certain methods even in scikit-learn that are not backed by the C++ implementations. One concrete example that I've ran into is the cover tree. The cover tree is an algorithm that you will use to feed the k-nearest neighbors algorithm to your data. And in Python, the cover tree is implemented in Python. So you will get some performance improvement if you switch to the Rust implementation. And you might find, you might find some, if you look under the hood, you might find some examples where you will get an improvement in performance when you will migrate your code into Rust. But I would say that's my 5 cents on my comments on that. Okay, so I think the rest. So the 10K unit, I'm not sure, frankly. As I said, I'm not sure about the unit of this data set. You can check this online. I think they should have this information on the. There's a website, UCLA data sets, as far as I remember, where all these data sets, including the Boston housing data set, are present, and there is a little bit of a description about each data set.
Yeah,
So
that wasn't so much a question as it was just a guess at when you were talking about the units earlier. It's not important.
Might
Thanks.
be, and that's an old data set, so the prices are not necessarily up to date, obviously. So yeah, let's talk about logistic regression. That's the last method I want to talk about, and the reason why I want to talk about it is because it uses a bit different method to find the estimates of the model parameters. But first, we need to talk about the model itself. As in the linear regression, the equation is the assumption is still the same. We're still assume that there is a linear relationship between our predictors and the outcome. But in this case, even though it's called a logistic regression, what we do, we actually build a classifier. And if you remember the classifier, in classifier, we predict either binary or multi-class outcome, where the outcome is, for example, might be fraudulent, non-fraudulent, a binary outcome, or red, blue, or the outcome might be, for example, if we are trying to predict the location from the price, for example, of the house, then the location will be an example of the multi-class outcome, where you have where you're predicting where exactly the house is from the price or other attributes of the house. So in this case, we can't use our original formula anymore, because our original formula gives us the quantitative outcome, gives us a number. So the question is, how do we go from this number that linear regression predicts to the binary outcome? And the standard way to do that is, one of the ways to do that is applying a sigmoid function. If you have a multi-class, for example, you actually would need to use another function. It's called the softmax function. But in this case, I will just talk about sigmoid functions. Why? Because the formulas. We'll talk about the optimization later, but if we'll go with the sigmoid function, the formulas for that we'll use to optimize, to find the parameters of the model will be a little bit more complex. But what the sigmoid function does, it takes the numerical outcome that is provided by the x multiplied by beta's equation, and it fits it or squishes it between 0 and 1. So that, for example, if you have something really if your logistic regression predicts really small, really big negative number, it will become 0, and if it's a really big positive number, it becomes 1. And that's the formula for the sigmoid function. So now with that, I'm gonna go to the Python again, and we'll quickly go through the method that fits logistic regression to other data set this time. So the data set that we're going to use is credit card fraud detection data set. I took it from Kaggle. So what it contains, it has the, let's see. So I'm reading this data set. So what it has a transaction that is represented by 30 numbers. I don't know what these numbers are. And there is a little bit of description on the website here. If you click on that, there's a little bit of description about how they got these numbers, but it doesn't really matter. What we're trying to do, we're trying to use these attributes to predict the class of the transaction. 1 represents fraudulent transaction, 0 represents non-fraudulent transaction. And once again, we're going to do the test train split of the data set. The data set has around 1,000 rows, 1,000 transactions. Each transaction, as I said, represented by 30 columns, 30 numbers. And of course, we have the same number of outcomes. And when we split that into train tests, we have just 700, almost 800 rows for training and almost 200 rows for testing. And then we're going to apply logistic regression to this data. Once again, we are using scikit-learn's out-of-the-box standard logistic regression class to do that. It's very straightforward thing to do in Python. We fit it, we get our estimates of the class values, and the function that we're going to use to measure the performance of our model is called AUC. For sure, it's called AUC, but basically the idea is that we are building. We are looking at the two values. We are looking at the anyway. So I was thinking about how to explain this function better, but maybe it would be a little bit easier if I'll show the curve here. So if I'll just make it bigger so that everyone can see, basically what we're trying to do with AUC curve is we are looking at the true positive rate and the false positive rate, and we are from our known outcomes and the predicted outcomes, we are building this curve. And the idea is that then we are taking the area under this ROC curve. And the bigger this area, the better, because if the area is really, really large, if it's, let's say, 99 or 93% of this rectangle, if it covers 99% of this rectangle, that means that both the false positive rate and the true positive rate are good. If it covers just 50%, that means that our predictions are not better than the random chance. And I think that's the best way I can explain the area under the ROC curve. But in our case, for our purpose, what we really need to look at is the value of the number. If it's not far from 0.5, that means that our model is not really good. That means that whatever prediction that we are making, it's not going to be better than the random number generator. If it's close to 1, if it's 1, it's also better, by the way, because it indicates that something is wrong with the model. So the ideal scenario that I've seen so far is somewhere around 0.94, 95. That's the healthy number that we want to get. Sometimes 0.7 is also good. It all depends on your baseline, of course, what you're comparing with. And when we run our AUC curve, area under the ROC curve against our predictions, what we get is 0.94. That means that our model it's doing a great job of differentiating between the fraudulent and non-fraudulent transactions. I think there were some questions. Yeah, that's right. Area under the ROC curve. ROC, that's a receiver operating characteristic. If it tells you anything, because it doesn't tell a lot to me, frankly. I think that's one of those characteristics that have been used prior to machine learning. The history goes back to, as you can see it here, it's to 1941. So the machine learning people, they borrowed some of the ideas here from this from the people who've been using the receiver operating curve characteristic before. And anyway, let's go back to the Python. And by the way, that's all about the Python side of it. So we feed the model, we've got our estimate of the performance, we've got our I hope I do bring the parameters. Let me check. Oh, maybe I don't. That's bad. Anyway, it's not a big deal because the way we'll compare the model that we'll get in Rust with the model that we get in here is through this AUC score. And now back to my slides. In Python, in Rust. So how do we find the estimates of the parameters of the model? How do we find the estimates for the beta? The reason why we can't go with the same approach we use for the linear regression is because of the sigmoid function. So the sigmoid function, it brings nonlinearities into our equation, and because of that, we can't really apply linear algebra methods to find the estimates of the parameters. So instead, what we need to do, we need to go another way. And by the way, you can use the same approach to find the estimates of the linear regression as well. This approach is an optimization, of course. And what optimization does for you, it basically uses a variety of methods. Some are derived from the calculus, some are derived from just simple ideas. that you need to go downhill to optimize any function to find the values of the parameters that gives you the best fit for your data. What I mean by the best fit of my for my data is, let's look whether I have it here. Yes, I have it here. Great. So when we are optimizing some function, in this case, what we want to find the values of the parameters, the values of the beta that will give us the best possible outcomes, the best possible values for our dependent variable, for our fraud versus non-fraud values. And we know the true values, right? We know that each transaction in our training set comes with the fraudulent and non-fraudulent. So what we can do, we can build a function that will compare the predicted outcome with the real outcome, and will spit out a number that represents how far we are from the true value. And if we average it over the entire training data set, we get some value that will tell our optimizer, or the function that finds the values of our predicted, finds the estimates of our model parameters. It will tell this function where to go, how to, whether we need to drive the values of the parameter lower or higher. Since we are using the derivative-based method to optimize the function, we will also need the derivative of this function. So that's our cost function. That's the function that tells us how far we are from the optimal value for our parameters. And this is a derivative that tells the optimizer where to go, what direction to take. And another thing that I want to say is that unfortunately, there's no straightforward way in Rust to get the cost function from, I don't know, from the method that you want to use. So if for each method, let's say it's a logistic regression, or SVD, oh sorry, no, or some other, or let's say, or a generalized linear model that uses some other assumption on top of your data. Each method will require its own cost function. But the good news is that if you Google and search around, you'll probably find the cost functions that are being used by the different by the standard libraries like scikit-learn. So this function, for example, I found it directly in the web. That's not something I came up by myself. And the derivative, the good news is that in Rust, there are libraries that can help you with the derivative. So you don't really have to find the derivative yourself. There are methods that you can use to automatically find the derivatives from the cost function. They are called auto differentiation methods. And don't have any concrete examples right now. But I think the library that I'm using, this argmin, it comes with an option. You can actually use a compilation option to automatically derive derivatives without the need to calculate them yourself. And another thing that I want to say is that if we, for example, so that's the cost function for the sigmoid function. But if we'll go with this multi-class classification and the softmax, this cost function will be more complex. So that's the sigmoid implementation I'll use in the Rust, and that's and that's just an example of what happens when I apply the cost function to my data. Actually, to two values. The first one is the actual value. Let's say we have an example, a sample where an example of the fraudulent transaction. So that's our 1.0, represents fraudulent transaction. And let's say our logistic regression predicts the very large number, which will be transformed by sigmoid into 1.0. So in this case, in this particular case, for this particular sample, our model is doing a great job of predicting the class of the transaction. So what will happen if we apply the cost function to these two values? We will get a really, really small negative number that tells our optimizer that it got really, really close to the optimal parameters of the model. And when you average that over many, many samples from your training data set, you will get some average number. And this average number will this average number will force the optimizer to slow down and converge on the parameters that it currently uses to calculate the cost function. That's an example of what happens when we are predicting the incorrect result. When we're predicting incorrect result, this number becomes really, really large. It forces the optimizer to make bigger changes to the parameter values. In the next iteration, the hope is that this change that it makes right now to the parameter values will drive this cost function down. So that's an iterative approach that is being used by the optimizer to find the optimal parameters. So let's actually go to some real code and use argmin library, the Rust library that is available for anyone who wants to use. Let's use this library to find the optimal values of our logistic regression. And the particular method that I'm going to use right now, the particular optimizer that I'm going to use right now, it's LBFGS. Each letter in this method name represents initial of the person who invented this method. That's the method that is being used by default in scikit-learn to find the parameters of the logistic regression. But you can use other methods, so you're not restricted by this particular method. You can use, I don't know, some non-derivatives. For example, one of my favorites is the CMAES. Let me actually type it here. CMAES. It's the derivative-free method that it works really, really great if you have non-convex data with a lot of local minimums. So you might want to consider that. And the good news is that the argmin, as far as I remember, supports this method, or at least there is the pull request that where the person who created it wants to bring it into the argmin library. So what we're going to need to do to apply the argmin to optimize our to find parameters, we'll need the loss function defined as a struct, and the loss function has contains the training data. And it has two methods. One is apply, that's the forward calculation of the cost, and the gradient. As I said, as far as I remember, there's a way to automate this function, so you don't really have to implement it yourself. But here I've implemented it just to show how what would I do if I need to implement it myself? So that's we're implementing this trait for our loss function. We are optimizing on the entire training set. And here is just the straightforward implementation of this function that of this cost function that sorry, not here. Maybe it was here. Yeah, this one. So that's the straightforward implementation of this function. You can examine, sorry, not this one. You can examine this method later. I'll share the code with you at the end of the presentation. But trust me, that's just straightforward implementation of this function. That's a gradient. And what we do next, we are taking our loss function. We're setting some initial parameters in this case, pretty much zeros. That's the initial value for our parameters. That's the parameters of the model that we want to find. And then we are setting up the particular method that we're going to use, the LBFGS. They call it solver in argmin. Finally, what we're going to do is we're going to use the driver to run the solver on our data with the initial values of our parameters. We will run for just 100 iterations, and once we're done with 100 iterations, we are reading back the values of the parameters that we were optimizing, and we split those into the two vectors. The one is going to be the coefficient, and the other one is going to be intercept, just like we did for the logistic regression. What I want to mention here is that you don't necessarily have to run it for exact number of iterations. I think there are certain conditions that you can set. For example, if you found that the values of the parameters don't change that much, the absolute change from one iteration to another is, let's say, below a certain number, you can terminate. Or if because we're using gradient-based method, the other way to stop early is to look at the gradient, how the gradient changes. If the gradient changes not so much, we also want to terminate early. But in this particular case, it's just a straightforward 100 iterations. And we found our values, our parameter estimates. And let's see how does it compare with how the performance of the model compares with the Python implementation. And in order to do that, I'll actually need to implement my predict function. As I said, the logistic regression is not that much different from the linear regression. All I need is to do the linear combination, to run the linear combination for each sample with the coefficients and add intercept. But then on top of that, I need to apply this sigmoid function to each row to make sure that the values that I'm predicting are all between 0 and 1. And these are my class values. These are my estimates for the class values. And finally, when I run the AUC on top of this, using with the test set, what I get is the value, the AUC value that is actually quite far. So I would be, if I were deciding between using more optimized Rust implementation that runs faster and the Python implementation that gives me, in this particular case, better performance, I would probably go with Python, just because even if you're going to run faster, you still don't want to sacrifice in precision. So in this particular case, I think it's worth exploring more why there's a difference. I would say probably there is a difference if you play with parameters of the optimizer. What I'm talking about are these parameters. and maybe also with the stop condition here, you would probably be able to get performance that is on par with the Python implementation. In this particular case, and once again, there is you need to remember that the test train split gives you slightly different data sets all the time you do that. So in this particular case, since the data set is small, I would go with the cross-validation to look at the average performance to the better estimate of the performance and compare that against the Python implementation to get the feeling of where I am, how far am I from the best parameter values. Yeah, that's pretty much it. I don't think I have anything else. And the final note is, sorry, let me show that. Interesting. Oh yeah. So final note is you will find the code on my GitHub account. I'll share the presentation later today through the meetup page. So that everyone can go and examine the code. And so, yeah, if you have any comments, feel free to send me an email. Or, in fact, if you have any questions right now, I'll be glad to answer those.
How did you go about like unpacking let me rephrase this. Do you think the Rust libraries try to have at least mimicked some of the API surface of the Python libraries to try and be portable or have your knowledge be portable? Or do you think it's a lot of novel kind of interactions with various functions?
Well, unfortunately, you can't really copy a lot of the functionality that comes with the Python provides. You can't do the dynamic. You can, for example, create a function that can be applied to strings and numbers and floats all equally in Rust. So people have to go with the slightly different API. But what I've seen in NDArray, they try to mimic the look and feel of the NumPy. And there's also, of course, the question of mutable references and references, right? So you need to be really, really careful about what type of the functions you're using. For example, you don't want, if you're taking a slice of the array, you don't want to turn that slice into the own representation, because in this case there is a necessary copy that happens. So there is a separate functions in the NDArray that deal with the how do you work with the slice, how do you work with the mutable slice, because that's how you get better performance compared to the I don't know, or maybe even sometimes Python. But in general, yeah, I've noticed that for some of the, well, it's probably only true for the NDArray, and Algebra goes on its own path here, and some other libraries like argmin. It's I don't think it mimics any of the existing Python libraries that are out there for optimization. At least maybe it does. At least I don't know. I don't know what library it mimics.
Thank you.
Have you used the like Rust tools for work or a side project? Like, have you used them for any projects other than just like seeing to what extent you can do the same thing that you can do in Python?
Yeah, that's a good question. I think so. The reason why one of the reasons why I've decided to implement machine learning library in Rust is it all started from the one implementation of the cover trees that I wrote to speed up one pipeline at work. And the reason, as I mentioned before, I found that the Python implementation was, while it was correct and doing what I needed it to do, but it was really, really slow compared to the code that I run in Rust. So I end up using that algorithm at work and end up extending this algorithm, adding new algorithms and the machine learning methods into this library. But right now, I'm not really using any of the tools that I wrote or any of the machine learning algorithms that I wrote in Rust at work, simply because it's hard to go. Like if your company has built all the tools, all the support around the idea that everyone uses Java, it's a bit harder to go with Rust. You have to work really, really hard to do that. It's not impossible, but yeah, it's not gonna save you time for sure.
So at a previous company, we trained models, linear regression models in random forests using scikit-learn, and then when we actually deployed them, we were using a pure C implementation for inference. Do you think that could be a either easy or useful like paradigm where you maybe train your models using things that are more, or libraries that are more familiar to data scientists, and then when you actually go to deploy it and you need high performance, you take the models and deploy them using Rust?
Yeah, and by the way, that's a really good point. What you can do, and I think that's the right way to do that, is when it comes to finding the parameters, there is a lot of math and methods and some research that has to be done to figure out how it's done and translate that into Rust. And in a lot of cases, that's unnecessary, because once you've trained your model is compressed into certain representation. In the logistic regression, linear regression, these are the parameters that I've shown. These are the 13 numbers for the Boston housing data set, or 30 numbers for the other data set. For the random forest, you're going to have all these splits that are happening that you will need to compress into certain representation to be able to use when you're doing the forward pass through your model. And when you are doing the forward path, you don't have to do that because you already have your parameters. So what you can do, you can take those parameters that you learned elsewhere and use them in Rust. And usually the forward pass implementation is much easier than the training of the model. So if you can use Python or R or Spark.ml to train your model, you found your parameters, you can just save that model, take the parameters out of this language, and use those in Rust and implement just the forward pass. Just in the logistic regression, it would be just this linear combination or multiplication, simple matrix multiplication. In random forest, it's going to be once again simple traverse through the trees with the averaging at the end, and so on and so far. So I really recommend this approach. It's a really good approach. And also the question, there's a question of precision. As you've seen in this particular example that I've showed, a lot depends on parameters and particular implementations that you use to train the model. If you are not following exactly the same approach that people use in scikit-learn or elsewhere, you might end up with suboptimal values that are not as precise as they could have been if you were to use the other library, the library that has been reviewed and modified by many people who are actively involved in the machine learning, and read the latest papers, the latest results, latest tuning, and the additional optimizations that are that are required to get the best possible parameters in any particular case.